The last section in estimating stellar distances is by using cepheid variables. So, the nature of a cepheid variable. Here we have a star, which is the SU Cygni, which has a variable brightness, a variable magnitude. It basically goes from 6.4 to 7.2, 6.4 to 7.2. What happens, 6.4, well, remember 7.2 is a large number in the magnitude scale, so it's actually quite dim here, and it's quite bright here. So it starts off with bright, then gradually gets dimmer, and then gets brightened again very quickly. Starts off dim, bright, gets dim slowly, then quickly expands and gets brighter again. Then contracts, gets smaller, expands, and gets bright again. So cepheid variables are variable stars. The time period gives us an idea of what their intrinsic magnitude, the intrinsic luminosity is. So let's just review. I mentioned cepheid variables before. We looked at different kinds of stars, and they basically, the brightness oscillates over a few days. So it's a regular pulsing star, and it takes a few days for it to be bright and dim again and bright. So cepheid variables are stars of variable luminosity. The luminosity increases sharply and then falls off gently with a well-defined period. It doesn't change for a particular star. This period is related to the absolute luminosity of the star. And if we know the absolute luminosity, and we know how bright it appears to be to us, then we can work out what its distance is. A cepheid variable is usually a giant yellow star. It's normally much brighter than the sun. It pulsates regularly by expanding and contracting, resulting in a regular oscillation of its luminosity. The luminosity of cepheid variables range from 10 to the 3 to 10 to the 4 times that of the sun, which means it's roughly 10 times the mass of the sun. Remember, the luminosity is the mass to the power of 3 or 4. Explain how cepheid variables may be used as standard candles. Now you need to know that if a cepheid variable is located in a particular galaxy, you know the time period, you can work out its absolute luminosity, its absolute magnitude. Then you can work out the distance. Then you can work out the distance to that galaxy. So it's basically used as a standard measure for measuring distances, a standard candle. So the relationship between the cepheid variable's luminosity and its period is quite precise, and that's why it's used as a standard candle. We can estimate the distance quite well. And we've known about them for about 100 years or so. It was discovered by an American called Henrietta Swan-Leavitt, who did lots of research on cepheid variables around, well, 1912, just over 100 years ago. And there she is. Remember, it's brighter than the sun, much brighter than the sun. It's a yellow star, which means it's got pretty much the same spectral appearance as the sun, but it's much brighter. So on the HR diagram, this is the sun, and the cepheid variables are much higher. They're not actually main sequence stars, but they're much brighter than main sequence stars. So this is where the sun is roughly, and the cepheid variables are here. This is called the instability strip. These stars here, they are our Lyra variables, and the cepheid variables have oscillating surfaces, so the brightnesses change with time, periodically. So here they are. This is where the cepheid variables lie. This is an instability strip, and the sun is here. Here's a particular galaxy, for example. How do we find the distance to this galaxy? Well, here, in this part of the galaxy, there's a very, very bright star, which is a cepheid variable. With the telescope, you're able to observe it over a few days, and you're able to see what its time period is for the variation in its luminosity. From that, you're able to find out its luminosity, and then you're able to work out its distance. You know that these stars are in this galaxy, and therefore you can work out the distance to the galaxy. Here's an example where you notice that it goes from 14 to 14.5 to 13.5, so it gets brighter. This is apparent magnitude, smaller m. Remember, the absolute magnitude is much bigger than that of the sun, so it gets brighter very quickly and then gets dimmer very slowly. Brighter very quickly and dimmer very slowly. And what is the time period of this? Between 1 and 4.5, so it's roughly 3.5 days. So what is, if we know the time period, 3.5 days, how can we find out the absolute magnitude of the luminosity? So a 3-day period cepheid is roughly 800 times as luminous as the sun. A 30-day period cepheid is 10,000 times as bright as the sun. So it's a much bigger star and has a longer period. So by measuring the distances to cepheid variables nearby, we're able to work out what their luminosities are and work out this relationship. They're high luminosity, and it enables us to see stars which are a long, long way away and galaxies that are far away, and we're using them as standard candles to find out the distances to clusters and external galaxies. Here's a relationship. For example, we spoke about a period of 3 days. We can find out that luminosity is roughly 10 to the 3 lots as much as the sun. If the period is 30 days, its luminosity is 10 to the 4 times the sun.